Today we're going to go a bit further in our exploration of PCI Express with this little device over here. So let's find out more. So in the previous video we used this PCI Express extender, single lane, but that has all the components necessary for PCI Express to work. And we just intercepted one of the wires of the differential signal of the reference clock. And I decided to improve it a bit. I bought a longer cable, and I intercepted not only both clock wires, also the PCI Express lane themselves, both wires. And let me zoom in a bit. So the idea is to build simple, as much as I could, simple PCI Express breakout board, connecting to each of the copper lines that we are interested. Currently I'm interested in the clock signals in both of the wires, but perhaps in the future I have a way to explore the data coming through the data lines. So this is just a simple prototype circuit with using some SMA vertical connectors. The vertical connectors are very useful because they have we'll see now when I turn the board around. They have the pin in the middle that is helping me to connect to the copper. Try not to cut the copper. Just making sure that the wire goes across without breaking. Just connecting the tip of the connector into the copper. So let's get a look. So something I try to do an extra effort is on the ground plane, because in this method of extracting PCI Express from a motherboard through a USB cable, the ground is only managed through the shielding of the cable. In the USB standard, those two cables we see here are the power. So there is a way to manage the ground across the cable, but not in this case. As I mentioned in the previous video, this method of extracting PCI Express repurposes the USB cable, but throws the standard through the window. So don't be confused. Don't use this type of cable or this type of tools to do anything related with USB, because it's not USB. In fact, the cables, the wires that in the original standard are managing the power, in this case they are repurposed. I think one of them is the wake signal to wake, so a PCI card can wake up the motherboard in case it's suspended. And the other, I don't remember what it is. It's not important. The important bit is that those cables are not powered anymore. So the only way we have to share the ground between our PCI Express card and the motherboard is through the shielding. So I put an extra effort to make sure that the shielding is making contact and is soldered to the ground plane in this board. It's putting as much wires as I could. And it's not easy. The metal, I don't know which metal it is, but the metal that is used in this shielding is not designed to be soldered, so it's a bit tricky. Yeah, before I forget, this cable is from the brand Cable Matters. I bought, I guess, the most expensive one I could find. So I made sure that it was a good cable, because we not only we're doing new things with it, we are also extending the length. If you recall, the one that we used previously, the one that comes with this kit, is much shorter. So I decided to make it longer, to have better options, to be able to keep the PC farther from the desk. So anyhow, all the shielding as much as I could into the ground plane, and then putting both, so peeling a long, well, not a long, but peeling a piece of the cable, peeling it off, and then put it back together. So as you can see, in order to have some room to work here, the idea is well, the trick, we can call it, is just to push everything together and bending the wires to one side, bending the wires to the other side, and keeping the clock wires in the middle. And then with a bit of patience, with the soldering iron, melting away the protective plastic, putting the cover copper on top of the central pin of the SMA connector, and soldering. Let me see if I can find. Yeah, I still have some left. So this is the SMA connector we're talking about, with the pin. All right. Obviously, the sides go to ground, and the center goes to the copper. A word of advice, if you try to do this, is that it's important to put some solder first in the pin, because when you're later dealing with here, everything is kind of tight, everything is a bit messy. So it's good to have everything, is to solder. The method I use is to soldering the connectors first, all of them into the board. Then patiently align the wires to where the connectors are, but it helps a lot to have a bit of soldering already into the central pin. So the moment you approach the copper, and with a bit of soldering, it gets attached pretty quick. Something that I also try to do is to keep things symmetrical as much as I could. When I'm bending one wire to one side, trying to keep the other right on the opposite side, not soldering in different places. It may not be important, but the idea is that you want to intercept both wires at the same point, because remember, those are differential signals. So yeah, that's the idea. If you connect to the wire in different places, if I connect to this one over here and the orange over there, when I extract the signal, they won't be perfectly aligned, and that could have an impact on the measurements. Obviously, mm, we we we're going to have a number of other problems here. So it's not not achieving for perfection. We're going to have a number of problems. So, but the idea is that to keep it symmetrical, it's not a big task, and so at least among all the problems we're going to have extracting signals like this, we'll have one problem less. So this is the board, and now let's play a bit with it. We have now the USB cable connected to the PCI slot. We have the board power up, an old Ethernet card will suffice. And a couple of SMA cables. Let's just plug them into the oscilloscope and see what happens. And here we have it. It doesn't look great. We need to keep in mind that we expect 100 megahertz signal, but its spectrum has been spreaded. We talked about this also in the previous video. So it's not going to be very stable. It's made on purpose, and I guess we also don't have a very professional setup here, which is also helping. Let's measure for curiosity. Volts peak to peak, channel 1. All right, and also frequency in channel 1. (300 millivolts up and down), and 100 megahertz also up and down, kind of expected. And we can also experiment and say, okay, what happens if we add both sides of the signal together. We add channel 1 and channel 2. And the result doesn't make much sense, to be honest. So apparently adding is not what we need. Let's try subtracting. And this resembles more what we have at the source, which is, I guess, kind of what the PC receiver does on the card to reconstruct the signal and getting rid of any interferences that happen putting the transmission line. All right, let's try something else. 1 second. So just for science, let's see what happens if we plug into one of the data lanes. Okay. Yeah. I suspected this is gibberish. The card, the PCI Express card connected over here is an old, very old Broadcom Ethernet card. Should be working at Generation 1, PCI Express Generation 1. So I expect here at least to have 2.5 gigahertz of signal. And we are not ready yet for that. But that's how it looks. And now we know. I hope you enjoyed. See you next time.